Imagine a blackout that spreads across an entire region, or a financial crisis where the failure of one bank triggers the fall of many others, or even a biological system where one mutated gene sets off a chain of cellular breakdowns. These are all examples of cascading failures, when the failure of a single component in its complex system triggers a chain reaction leading to widespread collapse. Understanding cascading failures is crucial because robustness is the difference between a system that bends and one that breaks. In biology and medicine, robustness helps us understand why some mutations cause disease while others don't. In social science and economics, it explains how societies survive or collapse under stress like war, famine, or financial panic. In ecology, it helps predict when ecosystems might tip into irreversible decline. And in engineering, it's the foundation of safety, designing planes, bridges, and networks that can still function even when parts fail. At its core, studying cascading failures helps us answer one big question: what makes a network resilient? To measure robustness, scientists often use percolation theory, a branch of statistical physics that studies how things spread or break across networks. Here's the idea. Imagine a network where each node is randomly removed with a probability p. At first, the network stays mostly connected, but as p increases, we hit a critical threshold ps beyond which the network suddenly fragments. Mathematically, we describe this with the order parameter p infinity, which measures the size of the largest connected cluster. When p is less than ps, most nodes are still part of one giant component, but when p is greater than ps, that component collapses. This transition from connected to fragmented is called a percolation transition, and it mirrors how robustness breaks down in real-world systems. Now let's look more closely at how percolation actually unfolds. Here we have a square lattice, a simple grid where each site can either be active or inactive, depending on the probability p. At low p, like zero point 0.1, only a few sites are occupied. Small, isolated clusters form, but there's no large-scale connectivity. As P increases, more sites activate and more clusters begin to merge. At a critical threshold called PS, these separate islands suddenly connect into one giant component that spans the entire system. This marks the percolation transition, the point where local connections become global structure. In scale-free networks, a few nodes, called hubs, have many connections, while most nodes have only a few. These hubs are what make scale-free networks incredibly robust to random failures, because most random node removals hit small nodes, not hubs. But this robustness comes at a cost. When we deliberately attack the hubs, everything falls apart. This is called attack vulnerability. If the largest hubs are targeted, say, a few key power stations in an electrical grid, the network collapses dramatically faster than under random failure. So scale-free networks are like real-world societies. They're strong under chaos, but fragile under intent. The balance between robustness and fragility defines how real systems survive shocks or spiral into chaos. Up until now, we've assumed node failures are independent. One fails, but it doesn't directly affect others. Reality, it's far messier. In real systems, nodes depend on one another for power, communication, supply chains, even survival. That means one node goes down, its neighbors lose support and may fail too. That's a cascading failure in action. Think of the 2003 North American blackout. A single power line sagged into a tree, tripped offline, and triggered a chain reaction that cut power to 55 million people, or the 2008 financial crisis. So how can we prevent cascading failures? 1. Add redundancy, extra connections or backup nodes that keep the system stable when one fails. 2. Decouple interdependent systems, so failure in one layer doesn't instantly take down another. 3. Monitor hubs carefully, since they're points of both strength and vulnerability. 4. Design for graceful degradation, not perfection. Allow systems to fail safely, not catastrophically. At the end of the day, cascading failures remind us that complex systems are only as strong as their weakest connections. Here, we'll summarize the mathematics of network robustness. or how likely a network is to stay connected as nodes fail. The first equation, the Molly-Reed criterion, says a network has a giant connected component if the average of k squared divided by the average of k is greater than 2. In simple terms, if a few nodes have many links. The next formulas describe what happens as we remove nodes. For random failures, the critical fraction FC tells us when the network breaks apart. And for random networks, that threshold depends only on the average degree. When FC is higher, the system is more robust. Attacks, however, lower that threshold dramatically by targeting the most connected hubs. Finally, the last equation shows that cascading failures often follow a power law, meaning small collapses are common, but once in a while, a huge one can take down everything.